Yeah. Thank you.
Thank you, Carmen, and of course thanks to Miha, Argir, the other organizers for the invitation to speak here, and also more generally Valerie, invitation to spend time here at the Newton Institute, which I'm enjoying very much. Well, one of the few things in this beautiful workshop maybe missing a little bit are molecules, as it were, and I hope to introduce some during the talk. The idea is to talk about optimizing materials, but also understanding better this organic functional material, including liquid crystal, and in particular liquid crystal, with a view to device applications. And there are many, particularly if we think of liquid crystal, well, the obvious one, which is the liquid crystal displays, but also application in photonics, for example, this phase filters or these waveguides, and very interestingly in organic electronics. So I'll try to take a few examples of this and show you with some of recent result what can be done, what we think can be done. So bottom up means that we start somehow from microscopic, ideally from real molecules, and we build our way toward practical things. So many of the talks that we heard do not really deal with molecules, they deal with this continuum limit. But on the other hand, as you go down in scale, and one is going down in scale to nano, I mean, even the integrated circuits that we use are now kind of 15 nanometers, sort of. So one has to go down in scale, and there will be a limit where molecules become important. But more generally, molecules will be important if we want to choose a material and predict the properties. So the problem is very complicated, of course, and there are different time and length scale. So the atomistic, well, essentially this is Angstrom or nanometers. And what can be done? I'll show you some example now to actually predict real properties for real molecules is limiting the sample to order of magnitude of a few thousand molecules with all atomics to detail, which is enough for many purposes, not everything. Then you can lower the resolution, go to so-called molecular models. We heard some where you can have well, either spherical collection of sphere, Lennard-Jones, or only the repulsive part like we heard, or Gay-Byrne, where you have attractive and repulsive together with an ellipsoidal shape of different kind. And I will not really speak about this today, or lattice model, where you still have some reminiscence of going from micro scale to macro scale, but really again you have forgot the details of the molecules. So here you can take essentially, here we can take now a few million particles with effort, a few million particles, which is samples of the order of 100 nanometers sort of, which is good for example, organic electronics. Here you can take basically as many as you want, but certainly millions of lattice sites are not a problem. And this can still be useful for some application, also in devices. So for example, in a collaboration with electronic engineers from Rome, they are interested in making liquid crystal waveguides, and they have channels of polymer, PDMS, that we heard also here. And PDMS gives homeotropic boundary condition, and they want to know what's happening inside. And for this type of problem, simple lattice spin model, where basically you have some sort of cubic lattice, or could be other lattices, but cubic, why not? And you forget completely about the positional properties, so you cannot use it for simulating smectics, for simulating other things. But if you are only interested in the orientational properties, then you can take, for example, the simplest, which is a Meyer-Saupe, if you like, or Leibol-Lasher is the one that actually did it first in the 70s for nematic interaction, which is this one, is the nearest neighbor interaction between lattice sides. And you can confine with suitable boundary condition around. You can cut and make spheres, make a torus, make what you want. and then maybe you have a coupling to the surface. And so, for example, in this case, you could have your boundary condition and you want to know what's happening here, and then maybe you want to compare with experiments. So in this case, we still call it molecular, but the spin is not really a molecule. It's more likely a tight bunch of molecules who do not change their relative position through the temperature window you are looking at. And this is actually a good approximation, surprisingly. Maybe I'll show you later with atomistic that if you go through an isotropic to nematic transition, the first few coordination shells are essentially the same. Yeah, so there's very little difference between isotropic and nematic at the nearest neighbor at the short range level, which is of course also explaining why the density change are so small compared to density changing going from an ordinary crystal to an isotropic, and also the entropy change is very small. So this with false color giving you the orientation is similar, and then we can calculate the optical texture, and this is kind of experiment. Oh, sorry, this is simulated, this is experiment. So for this type of purpose is okay. And you could do it, of course, with continuum theory, and this is another recent example where we try to use simple modeling like this to interact with experimentalists and study together a problem which is maybe going beyond the very simple thing that you can do with continuum theory, but please correct me because it's not. So if we take an hybrid nematic film, it was mentioned also in some other talk, where we have conflicting boundary conditions. So this could be a few microns. Then you have homeotropic, vertical with respect to the surface boundary here, and say two-dimensional planar degenerate boundary here. This is a classical problem that's been treated by Oleg Lerventovich in particular, but other and probably people in the audience as well. And in the one elastic constant approximation, certainly this type of situation can be found, and we have also done simulation and the result match with this. So if the sample is small, you tend to have this kind of continuous joining of the two boundary conditions, or you can have the two classic plus minus one type defects. But what happens if instead of having fully degenerate disorder here, you have a control disorder that you want to imprint? And you can define a two-dimensional order by taking instead of P2, you are moving in two dimensions, you take the second Chebyshev polynomial. And we can do simulation varying this from 0, which would be full degenerate disorder again, to planar homeotropic, homogeneous, or anything in between. So we can do it easily with the simulation. We can do it in the one elastic constant like before, or if we want to see the effect, we can take a variant of potential divided by Hess and Lacaste and other, which is a kind of mesoscopic type potential where the elastic constant appear explicitly. And then basically again you put your boundary condition, you decide on some elastic constant on some surface coupling, and for example this is what we kind of predict from simulation for disorder. This is a rather large 200 by 200 by 12, large and thin sample. And then you can see, we have empty boundary condition around and to avoid, in this particular case, the effect of periodic boundary conditions that we normally use otherwise. And then we see the change in what you see at the polarized optical microscope, at least from simulation point of view. And then the group of Masa Ozaki and Hiroyuki Yoshida in Osaka, they've actually did imprint this configuration with a control planar order. They have, the sample, I do not have time to go into it, but it's kind of reasonably, I think, rather well known. They have a reactive monomer and azobenzene, so they can excite an image with polarized light. The azobenzene molecule, being like that, absorbs polarized light mainly with the direction parallel to the long axis of the molecule, so that becomes depopulated and the orientation comes out perpendicular to that. So anyway, they have made photopatterned region with an order similar to what we have, and that's actually their real experiment in polarized. So each of these should be somehow, of course, cannot be identical. It would be worrying if it was, because the elastic constants are different. This is a real experiment with boundary condition, blah, blah. But it is interesting that we can actually see that apart the similarity, we could ask questions and try to use this type of simple simulation as a kind of confocal computational microscope, so we can actually see how the defect evolve from a surface going up to the other surface. We can take layers, etc. And so, for example, we can calculate one of the metrics that in particular this Westin matrix, that is again based on the order matrix that we heard before, also John mentioned before for other purposes. And well, you can decide that you have a defect where one of these indicators is perpendicular. So, and Gregor Skačej in Ljubljana did apply some of this to the simulated morphologies, and you can see this is the first overlayer. You see defects here of opposite sign compensating, and you see here in the ordered one that the molecule, if you take a two-dimensional section, this is a kind of usual hyperbolic defect of one sign and of the opposite sign here. And if you put all the slices together, then you get this kind of filament or line. And that essentially shows that the defect that you see in polarized microscope from above, and then you don't know where the defect is originating close to the bottom boundary. So this is a type of modeling that doesn't really need molecules up to a certain point. But in most other applications for devices, the purpose is a lot more ambitious. And the purpose is, if you model, you want to propose a material or optimize a material, then as a very minimum, you would like to know if that particular material, which corresponds to a certain chemical formula, is going to be solid, liquid, gas, at the temperature the device is operating, so at room temperature, which is reasonable. And you would like to calculate properties. You would like to predict transition temperature and see if they are in the right place. Otherwise, what are you modeling the thing for? And the properties, and which chemical structure is preferable? Now, we cannot really say that one structure is the best, but the question that people in industry, at least in European projects, put to us is, okay, we give you 10 molecules or 20 molecules. Can you put them in order of preference for us? Can you tell us which should we try first? And notice that it wasn't obvious that one could predict phase transition, etc. I mean, I don't know if that is obvious. Yesterday, Tom, in this very nice review or summary of the report, mentioned that in some areas in solid state, certainly single molecules, certainly in certain solid state area, DFT basically has the solution, but not here. There is no theory that can give you, if I give you a molecule, even simple, say benzene, and I ask you, okay, fine, you can do all the calculation of the energy level, just go to your Gaussian 90 or whatever, you just, yes, push a button, do a little bit of theory, because you're not just operating on the machine, and you get single molecule property. But if I ask you, okay, I want to use benzene, or whatever, what is the transition temperature? What is the boiling temperature? And you cannot answer to that. Yeah, you have to do simulation, because it's a many-body problem. And at the moment, the problem is there is no theory. You have to do simulations. And the problem is not easy. And this is shown, for example, by this old example of Gray. Is old, but I think makes the point. We are used to the fact that if we change a little, then the result of what we do will change a little. A linear regime. But look at these molecules. They are big, relatively big molecules. You only change one CH2, pretty innocuous group here. And then, as Gray showed many years ago, if you have 0 CH2, transition nematic isotropic is 280 sort of. You put 1, it goes down to 50. 50. And now you add one more, it goes up again and down. So it's very difficult. I mean, you cannot say this is a little longer. It would give you the opposite result. Yeah, you have really to go through. And this can be done by simulation, but only since sort of 15 years. And the simulation in principle is not difficult to understand. You have your quantum chemical calculation by one of the many packages that exist. If you are in the Netherlands, you maybe use ADF, or if you are surviving the Gaussian license, maybe use Gaussian, whatever. Or you develop your one, and you calculate the single molecule properties. Then you have to, which includes torsional potential, because this is not rigid, this is flexible, and then you devise or modify the set of interaction, the force field. And then basically you have to solve Newton's equation of motion for these molecules may have maybe 50 to 100 atoms, and if you want to take maybe 1,000 molecules, then you will have sort of 100,000 Newton's equation of motion to solve, but that's okay. You have to do it you have to be very patient, because with the integrators available, the time step from one configuration to the next one is separated by delta t of the order of 10 to the minus 15 seconds. And you are interested in going at least to 10 to 100 nanoseconds, which means, really it's months of simulations. But anyway, and the terms are, just the intramolecular term with all the vibration, the spectroscopic, and the Lagrange has been mentioned, used for non-bonding interaction, so they don't overlap each other. They have a repulsion, you have an attraction, and of course you have Coulombic. So very quickly, I'll give you an idea of what is certainly doable now. So if you take the cyanobiphenyl and you want to follow the simulation, maybe you work out an order parameter, and again you have your ordering matrix that you are familiar with, and you have to decide on which is your axis U. The molecule is not really uniaxial, but you can take an axis of, for example, the minimum inertia tensor principal value, or you can take a fixed molecule axis, and then you work out your ordering matrix, you diagonalize it, and you take the scalars, the eigenvalues, which are rotational invariant. So if during the simulation your director fluctuates, you don't bother too much, and you can calculate your order parameters. And how do you locate phase transition? Well, it's a bit the inverse of the double well that we have seen in the Landau type theory of phase transition, isn't it? Where you have a double well of the free energy. Here, if you look at the order parameter, but you can do it with the energy, of course, then if you are a bit far away, you have a Gaussian. So, sorry, let me say. So these are different simulations at different temperature. Rather than just using the average order parameter, these are histograms of all the occurrences of the order parameter during the simulation. And you can see clearly, this is HCB, but you can do it for everyone, that here there is a transition because the system has kind of a jump from a peak of the order parameter here to here. And of course, if you were hitting exactly the transition temperature that you cannot because you don't know it, then you would have a double well or double peak here rather. But you can locate the thing, and actually it works well a posteriori. Once you have developed a force field, we can get it in. We can do better now, but it's of the order of 3 degrees from experiment, 2-3 degrees from experiment. This may seem disappointing, but I can guarantee you that it's quite not easy to obtain, and enough. You can get. Sorry, let me just comment. The temptation could be to go to your computer lab or IT, say, do you have an MD program? Can we just use it and push a button? You get numbers. But if you do not optimize the force field, the results can be rather disappointing. So these are 3 very respectable groups, and JCP, PRL, etc. And the result in small letters on the transition temperature, which was not optimized in that case, is sort of 80 degrees, 40, 50 degrees. Would you consider that satisfactory? I mean, if you want to do predictions, you have to bring your transition temperature to something which is reasonable. And then you can say, okay, I calculate the other properties, so density, order, NMR dipolar coupling, dielectric constant, etc. So once you have computer synthesized, in silico synthesized, like we heard yesterday, a compound, maybe you can do it for others. We are building a little library, so we've done quinquephenyl, sexythioneal, cinnamates, cyanobiphenyl, some discotic, triphenylene, etc. Now you can do experiments, like you would do real experiments. So for example, in all devices, practically, you work in thin films. So the interaction with surfaces is relevant, not irrelevant. So can we predict anchoring? Can we say, okay, I have glass, or I have a polymer, or I have a language blotted film, and I put my liquid crystal on top. Will it align parallel, perpendicular, tilted? Yeah, that's a reasonable question, isn't it? And normally it's answered only empirically. You just, yeah. So, so now, of course, like in a real experiment, even if you have now synthesized a liquid crystal, you need to synthesize the surface. And well, so we've again synthesized. All of these are published. So if someone is curious, I'm happy to give all the details. So we've done, for example, silicon. This silicon hydrogen terminated silica in the form of quartz or glass or rough glass, fullerene. Let's call this hard substrate. And then we've done soft surfaces as well. So self-assembled monolayers. And then you put the molecule on top. Will they align perpendicular? Will this be homeotropic or polymer? More, I mean, there's this kind of, well, how should I say, folklore that if you rub a polymer, the molecule will align along the polymer rubbing direction, isn't it? Is it always true? And what's the mechanism anyway? So I'll show you quickly two examples. So, so this is the first. It's a thin. So this is 6 by 6 nanometers, and this is a thickness of 10 to 12 to 20 nanometers. And these are very quickly the results of what you get. So this is the order parameter across the film. And you have two experiments. The thin sample stops here, and the thicker stops here. And each one has two temperatures, one isotropic and one nematic. And you can get messages, I think. For these surfaces, the order at the surface, at the interface, is basically the same, which means it's really dictated by surface interaction. Even the isotropic phase has essentially, at the very first layer, the same order. And then notice also that it's planar here, so we can predict that it is planar on this, and then it's homeotropic at the vacuum. Molecules like to stay perpendicular to the vacuum or air surface. I can tell you why. And we can get Rapini popular. The anchoring is normally expressed in this empirical form. And the way we can do it is we build a map of all the probability or frequency of occurrence of molecules at a certain position across the film and at a certain orientation. The cosine is given here. So you see the cosine 0 is populated, so it's 90 degrees for the normal. And then once we've got this, we can inverse Boltzmann, do essentially the log, and expand it or fit it, and you get your anchoring, which is stronger than many experiments. But look how quickly the anchoring strength goes down. 5 nanometers away, it's already decreased by kind of 2 orders of magnitude. And many experiments don't really probe the very first layer. So, so that's a way. And now you can ask questions like, okay, if instead of having silicon, if I have silica, and is it the same? And if I have a crystal, if I have a glass, is it the same? And if the glass is rougher, is it the same? So we can do that, and very quickly, if you have quartz, it's basically the same. So this is a 20 nanometer thick film, which is already amenable to experiments like the one that Igor has done with AFM some time ago. And again, so essentially as before. But if we have random degenerate, if we have glass, you see the effect is the opposite. The disordered surface, rather than the crystalline surface, is lowering the order at the interface, and then, of course, the order in the middle is recovered. And if the surface is rougher, it's even worse. And you can play with different surfaces. So is it true that if I have a self-assembled monolayer, and this is a self-assembled monolayer which attaches on the silica that we have just seen, and the molecules are, say, they are strongly bound to the surface, even though they can move horizontally. And you can, it's not enough just to say, I have the molecules on the surface and then I put the liquid crystal on top. It's very important to know the coverage of the surface. So if the coverage is very high, this kind of, it's not really a comb because it's very short chains, 18 and 6 in this case. But the molecules really like to lay on top of this dense self-assembled brush, if you like to call it this way, and they are essentially planar. You can lower the coverage. This is molecules per nanometer square. And then you have holes. The 5Cb molecule can penetrate the holes. And, well, that's a way, if you have many holes, to actually induce homeotropic. But it's very difficult to control. And also the distribution of holes is very difficult. So the other thing that we have proposed, and actually discovered that experimentalists do it anyway, is to mix long and short self-assembled monolayer chains, and then you have full coverage, but you will leave holes for the shorter chains, and this works. You see, the cyanobiphenyl penetrates and aligns the rest. And so this is shown here. That's the molecules laying on top of the self-assembled, and in this case instead they are penetrating and providing a template for the other. So again, I do not have time to go into the detail here. I prefer to give you a general idea, but I'll be very happy to discuss and be here not only this week but also next week in case. Now the other thing of the rubbing is so convincing, isn't it? You rub a polymer and the molecule align that way. And the cartoon that is often shown is, I think, is really misleading. It shows like ditches digged on this kind of field, and then the molecules are like logs and they lay. But the molecules are about, what, sort of, say, 2 nanometers by 5 nanometers. But the ditches that you can do with a cotton bud or something like that are probably not of that size anyway. So the model, and so anyway, is it true that they always align? So we took, that's the cartoon I was alluding at that I'm sure you have seen. This particular one is from Greg Crawford. But so we took PMMA, which is a common polymer, and polystyrene, which is another common polymer, and we prepare 2 slabs, one with the polymer disordered, amorphous, and the other with the top layer of the polymer sort of not really rubbed, lapped. In other words, we pull the end of the chain so to align the chains and mimic an ordered surface. I think you can see it here. The color just distinguish the molecules. They are not, in this case, orientation. So this is disordered, and this is ordered on the surface. So this combed surface mimics, and you do the same with PMMA. And then you sandwich 5Cb between these two, like here, and then you look for the director in the layer attached to the polymer here and here, and these are these 2 arrows. The continuous and dotted or dashed really are the top and the bottom director. And so if you have PMMA, sorry, if you have the disordered amorphous sample, you don't control the director. So it's basically on the 2 surfaces, it has different orientation. And okay, but if you rub PMMA along this direction, both the bottom and the top layer in contact with the surface are actually along the rubbing direction, as you would expect. But if you take polystyrene, it's the other way around. It aligns at 90 degrees, and which is sort of unusual. But if you look at the simulation, it is reasonable because of the chemical structure of the polystyrene, which is this has this phenyl ring sticking out of the backbone. So as you pull the backbone and the phenyl rings stick out, they make a kind of corridor which is very suitable to hosting the cyanobiphenyl into a perpendicular orientation. And this actually orientation has been found in a number of experimental papers. So this is showing the thing. So I think with low molar mass molecules like this one, and for sort of the range of application that you can call, say, optical devices, displays, or whatever, I think we are getting there. Of course, real display use mixture of 5 to 10 compounds, so doing real simulation would be horrible, but that's not for us. That's for, you know, really, maybe the industrial people there, they want to. But I want to show you some example also of two other things. I have still 10 minutes, right? No. For organic electronic application. And for example, you have, in organic electronics, you try to replace silicon, which is the king of semiconductors, with some organic electronics. So if you have a simple transistor here, this is so source and drain, and your organic semiconductor would be here, insulator, and the gate here. Then the point is, you can obviously put an organic semiconductor instead of silicon, and this would have advantages because you can put it on plastic, it's cheap, you can make it as big as you want. The manufacture can be done in simpler ways, but the advantages we know. But the point is that the mobility, the charge mobility, the mobility of holes of charges is very low. So if for polycrystalline silicon is the order of 1 centimeter square volt per second, let's see if a silicon crystal is kind of 10,000 times more. Pentacene, which is an organic material, one of the best, is about 1, but only if you have a very well-ordered crystal, which is nearly impossible to make. And so this is a problem. Liquid crystal have advantages from this point of view, both the rod-like or the disc-like, like this one, particularly because you can fill gaps with the liquid crystal. For example, suppose you have 2 electrodes separated by, say, a nano. You don't solder them, but if you have your liquid crystal and this, for example, these triphenyllenes or whatever, you cool it down, it forms spontaneously columns, and the column will touch whatever, they fill the gap. And the mobility is not very good, but it's strongly dependent on molecular organization. So if you are in the isotropic phase, it's a good, honest insulator, sort of 10 to the minus 4, 10 to the minus 5 centimeter square volt per second. But as you cool down, it goes up, and it goes up. And even if you are in the liquid crystal, and not in the crystal, which has the grain boundary problems that we heard, it's of the order of 0.1, sort of. So it's not bad. Now, we would like to provide molecular organization suitable for calculating charge transport property, and maybe then deciding which is best. So what are the problems? You cannot use rough models here because the charge, even in the simplest model, which is this Marcus-type model of hopping, goes from one molecule to the other, hops from one molecule to the other with this kinetic factor. Imagine this as a Markov process where this is an element of the transition matrix of the Markov process, where you have temperature things, but you have these transfer integrals which really depend on how molecules are shifted one with respect to the other, or even are rotated one with respect to the other, which boils down that you need to have the proper molecular organization and the atoms in place. So once you have that, and you have calculated your Kij, the probability of hopping from one side to the other, then you can do kinetic Monte Carlo. It's not difficult, so you start from here, and you see it hopping, and when it gets to the electrode or whatever, yeah, you collect many trajectories, sort of millions of trajectories, and you can calculate the mobility really by dividing the distance by the time it takes to get there. So detailed molecular organization and atomistic position. I just show you a couple of recent examples. This is for these triphenyllenes. It's work done in collaboration with Bath, University of Bath, Alison Walker group. And so we start from an atomistic simulation, view from top and view from side. And then, since we want very large sample, we make a coarse-grained approximation to this. And then we do simulation of sort of a few thousand. This is coarse-grained. We monitor that the G of R, the radial distribution, is similar to the smaller atomistic sample. And then we have, since this is rigid, we can have the atoms re-emerge from the coarse-grained. We know the position of the atom is stored there. And then Ian Thompson from Bath has done the mobility calculation with kinetic Monte Carlo. You can get real number. And this is low, but this is low also in reality, and is lower in the isotropic phase. So now you could say, okay, why all this fast if the mobility is low? Well, it's not always low. So, for example, if you take a smectic, it's typically also rather low, sort of 10 to the minus 4, 10 to the minus 5. But recently, a few years ago, this class of compounds called BT-BT have come out, and many groups, particularly in Japan, group of Hana, in Europe, Yves Gertz, and in the States also there are other groups that are studying this. Then the mobility is very high, I mean amazingly high, from 1 to 10, so this is already polycrystalline silicon, and there are reports that it is even 100, which is maybe, well, anyway. So one interesting thing is that Hannah made the suggestion, the hypothesis, that one key thing for this very high mobility, which is interesting for industrial purposes also, is the existence of a smectic key phase. The smectic key, I'll remind you in a moment what it is, but is a highly ordered smectic. So we try to do simulation of this one, not of this one, which is also, this one. And recently, this is work with Milan Politecnico di Milano, Milan Polytechnic, Guido Raus, etc., and our group. We have done simulations of this. The molecule is biggie, so it's not that simple. Well, anyway, so we developed some force field again, and this is, so we get the phase transition in excellent agreement of 1 degree. The nematic, sorry, it's not non-nematic here, isotropic to smectic in excellent agreement. And the order, here is the crystal. We cannot get the smectic E. We get a smectic A. I'll try to show you how, but okay, let me try to. So we calculate the obvious things, the radial distribution of the crystal, all the smectic points, and now we ask, what type of smectic is it? And so the transition from here to here is perfectly reproduced, in perfect agreement with the experiment. The spacing here is also in excellent agreement with X-ray, and this crystal actually, this was obtained from X-ray. We cannot cool all the way to this crystal, but this is like what you have in reality. It's very difficult to cool a mixture to a crystal if you don't take days or special measures, right? So liquid crystals are okay because they're still very fluid by the crystal. But anyway, so the layer structure is more evident if we color up and down with different color, red, than blue, and this is the structure, and this is the pair distribution showing this double bilayer structure up and down here. And is it a smectic B or A or C? So the idealized structure that we have is that the smectic A is like a two-dimensional liquid. The smectic B has this hexagonal order. The smectic E has the hexagonal order, but also short-range order. So we calculated the exactic order parameter and also tetradic order parameter, calculating the bond order around molecules. And you see the bond order is essentially 0, and then it jumps. So the phase is uniaxial. And but the mobility, that's the interesting thing. So so there is something missing in our force field because we cannot reproduce the smectic E. We have a very ordered smectic, but maybe not a smectic E. But the mobility still, you see, if you compare to the one we had before, which was the order 10 to the minus 4, this is in the realm of the experimental one. And so maybe the explanation that the smectic has to be a smectic E to give the very high mobility is not really necessary. Okay, I don't have time. No. Well, we've done a lot. I'll just show you a couple of slides. We've done a lot also on non-equilibrium processes. Well, a lot. We've done a little. Right? So we've modeled vapor deposition. And vapor deposition is one important process to fabricate this thing. So we've done molecular dynamics of this rainfall of molecules, for example, pentacene, another molecule on silica. And we follow the building up and crystallization of the layers, one after the other. And we can actually see the way the system is building up is multi-layer and test the different models that have also been mentioned here by Irene Fonseca, I think. This is the common growth and mechanism for deposition. So if the energy of attraction between molecule and substrate is very high, then you have wetting, this one, sorry. And if you have instead the reverse, then you have molds built in. And in any case, it is important to look at the probability that the molecule here, falling down on the first layer, goes down and wets the substrate, or rather stays up. And this barrier here is called Ehrlich-Schwebel, and we have calculated that. This is work mainly of Luca Muccioli and Gabriele Davino. And so you see, this is the silica, this is the first island of molecules, and then others fall in. We calculate the free energy by having many trajectories here, and this is a plot of the free energy, and this is a plot of the barrier, which is different from the first and the second. So, summary, I think the atomistic simulation provide a way of actually, maybe in due time, at optimizing material, because they satisfy at least the very minimum of this, that we can actually predict properties in agreement with experiment for real or realistic molecules. And also two fields that have been essentially left to experimentalists, to empirical things, that is surface anchoring and things like vapor deposition on equilibrium processes can be studied. And ideally, we would like to have all the way from molecule to device. And this is actually a collaboration with IMEC in Belgium with this. The only important thing is to mention, so for lattice model, Paolo, Cesare have done a lot. Surfaces, Antonio, Gabriele, Luca has done a lot. Silvia, Matteo for the programming, Otello for the surfaces, and Lara again. And collaboration with the people I've mentioned before, Osaka University, Ljubljana, Bath, and Polytechnic of Milan, and the agencies, and of course you, and apologies for 2 minutes, but we started 1 minute late, so thank you very much.
Yes.
Yeah, one question is, you said that you could get the transition within 3 degrees, and you say I can even do better than that, but I mean...
No, I didn't say, we published it, so yeah.
But one thing that, I mean, not that problem, but in similar problems, when you try to go that precise, then there are a lot of other things that you have to control, like, for example, I mean, a parameter, which is the cutoff for the Lennard-Jones interactions, for example.
Yeah.
And other things that are not really related to the force field, but rather to the way that you have to do the simulation. So,
no, I think these are under control. What is really important is, first of all, the finite size of the type of the class of question that you mentioned.
But for example, I've seen a lot of dependence on the cutoff of the Lennard-Jones, very sensitive to...
No. I think that is under control, and Lennard-Jones is well behaved. If you talk of Coulombic, okay, but we can do the Coulombic with particle mesh Ewald, and that is okay.
What cutoff do you use for the Lennard-Jones?
If I remember correctly, 3.5 or something like that. We can look it up, but I don't think, no, I honestly don't think that is the key problem. It's not the technical, the problem is really the force field is extraordinarily important. And I showed you some example of other group which did, I can tell you, professional work, and they are 50, 60 degrees out. But you can try yourself. You do simulation, you take amber or GAF or charm, you take a normal force field and you run through a simulation. And you see that it's kind of maybe 70, 80 degrees off. So, for example, our force field is used by Juan de Pablo in our group and the others. So it's not, it takes effort to do it, but it's doable. So 3 degrees, I think is reasonable. We can do better with a sample of sort of 8,000 molecules. We probably have 1.5 degrees, but that is so.
Okay, maybe you should continue with
Sure.
Thank you very much.